So thanks a lot for the invitation, first of all. It's a pleasure for me to speak here today. So a short intro, New Digital Craft. What are we doing? We're combining computational design skills with 3D printing, additive manufacturing, to create building products, new solutions for the built environment. And yeah, that's the focus already embedded in the name. The craftsmanship is something that we focus on to really use the tools to bring craftsmanship, you could say, back on the building side, or to just bring digital craftsmanship on the building side. So both is for us a key motivation, and it's always looking at sustainable aspects in that process. I want to start with the step 2 nest unit, the cadenza stair. We did in an open innovation project. So this is really only possible, a project to create this at the nest in open innovation research. So basically companies from the practice, but also research teams come together and basically bring their knowledge from the field into the project. So we realized this stair, designed by ETH Zurich, by Benjamin Dillenburger. I'm not going through the whole list. So what I was responsible, you can read it, it's published as well. I was responsible starting at BASF Forward AM back then. So being responsible for the formwork, so enabling a 3D printed formwork, a solution for this stair. So what is unique about the initial idea was to create a lightweight stair that can be handled by 2 persons, bring it on site, and assemble it on site. So this is clearly possible. And it's post-tensioned then with the refer post-tensioning steel. This is a new technology which also makes it possible to have it very intricate and small connections. You can see that here. So it's not possible with a normal post-tensioning method. It's a new method. And how it works, basically, so through heat, the steel that was here formed in a helix and 3 steel wires that were formed in a helix are heated by electricity. So high voltage heats it, and then when it releases, when it cools down, it actually gets the maximum final strength. So it's a cold memory steel. It's also a startup from the ETH there in the market already. And for sure, you can imagine it wasn't clear until really the last tests we did if the stair would hold the promises that we put into. So in terms of structural performance, but also in terms of this memory steel idea. So there were a lot of new inventions in it, in addition to the formwork that we developed, which I come in a sec. So we did test at the EMPA. Luckily, this connection with ETH and EMPA and the nest, you probably know the nest. It's very helpful in order to do these tests immediately and without questioning. So this was a great experience. So this step in itself has a 50% weight and material of the normal stair you know. It was a sustainable aspect in the beginning, but due to using a concrete that is also quite, let's say, and not a normal concrete, this becomes more or less equal. So we didn't make it the topic, but it's still valid for sure. And it was an initial idea for the design of the stair. So the wires that you see, the metal is only to prevent people from falling. So it's instead of a handrail, it's not holding the stair. So the stair itself is holding itself. You can see it on the left hand. So this was during the building process, which here it seems almost flying, but it's actually standing on a post at the bottom, and it's connected to the floor slab at the top. And it was pre-assembled and then put into place. And Rock Architects did the design of the unit and also coordinated this whole process on site. So it was very helpful to have them on board as well. And so here you see the formwork, which was really our topic then, our task. So choosing the right material, choosing the right technology to be able to have the resolution and also the form stability you need to actually create these intricate objects and how to combine them, and also how to create, let's say, a surface quality that the client, in this case, the EMPA or the nest wanted. So this is one of the pieces you see. And for sure we printed, this was first on a smaller printer at BASF back then. So now I'm using the Big Rep 1, which is also part of my production in the studio. And it's only 1 cubic meter. You can say it's for sure for building and construction a small volume, but you can already do a couple of things. So we're also combining the molds. So we print parts and assembling them, because anyway, we're using a coating on top, which can be removed and keeps the piece as well, not contaminated from the concrete. So you can actually recycle it and bring it back into a closed loop later. So this is clearly a lighthouse project, and it's a unique client. You need to realize it. So for me, it's important to also have building projects or building products that are also used, let's say, in a broader range. And this project came luckily where the client contacted us to use our technology to replace a stonemasonry work. So there were 10 windows to be made. And you can see for sure the production cycle is the same. In this case, we scanned an existing window to get the geometry and use a parametric way to, let's say, bring the point cloud into a buildable geometry, and then printed the formwork and casted it and assembled on site. So the reuse aspect is, in this case, the client wanted to keep the mold because we designed it so that we can replace different parts in the building later when they fall apart. So what you see at the top, so this is, by the way, the scanned part and the detailed part that we took in order to generate the geometry. And you can see at the top floor, these windows are still intact, but already some of the lines are degrading. So they want to use the formwork later also to recast it. So financially, this is interesting. For this client, it was the only way to actually rebuild this first floor. It was 10 windows. So you can say cost-wise, with 1 window, we are as expensive as a stonemasonry. So the first window after that, the second window is already cost-wise interesting, and we did 10 windows. So for the client, it was able to replace or to, let's say, rebuild the building in itself as it was, or to actually generate the aura of the design. And it was also funded even by the European Union, because she was able to, let's say, rebuild a structure in the center of the town instead of building a new building somewhere outside the outskirts of the town. So there's funding, clearly funding for this. So, and I started always looking into what can we do with the concrete. So what are possibilities to get a, let's say, less CO2 impact with the concrete? And I found clearly the geopolymer, which is the alkaline silicate bonded concrete. I will explain a bit more in detail. I hope I'm not going into super detail, but what you, just to understand what you have to see. So there's the cement concrete and the geopolymer concrete. Cement plus water plus sand and gravel, we all know it. It's the normal cement concrete. The geopolymer basically replaces the binder part. So it replaces the cement part. You also have to add water, but really very, very little, 1%. Plus sand and gravel, you get the geopolymer. And the fact, why do we use it? For sure, we all know the CO2 emissions, especially done by the industry, the building industry, is quite high and really under discussion. And from what my partner, of where I get all the mixtures of the geopolymers, tell, we are around 70%, 60% less CO2 emission than a cement-based or Portland-based concrete. So these figures, for sure, we will see later. We have to, let's say, test it with an LCA, but it is definitely something, because why is this the fact? Because the concrete, or what makes the cement, the concrete, so CO2 intensive is the heating of the material over 1,000 degrees. So you can see even 1,500 degrees over a really long time. And in this process, the CO2 is basically emitting, and also the energy you need to produce is quite intense. So this is replaced with a geopolymer. The geopolymer is more activated in a very lower temperatures on a smaller amount of time. And I'm not going into the full detail, but what is very important to understand is it always has a precursor, a so-called precursor, which is a solid raw matter, which can be fly ash, metakaolin, or a slag sand. So it's actually a rest material of iron production. And the activator, which is in fluid form, a water glass. And for me, the geopolymer wording is a bit misleading, because everyone immediately thinks it's a plastic, it's a polymer, but it is not. It's really a mineral-based material. And but just by the fact how it solidifies, which you can see on the right-hand side with the silicon, sodium, and aluminium elements, it has, let's say, structures that we know from polymers. That's why geopolymer, geo is also standing for that it comes from a geological base or a mineral base, so a silicate base. So we're doing tests, and I must say the performance is quite impressive. So we're getting very close to normal concrete, even depending on the mixture we're doing, going into the direction of high performance concrete, which we actually use for the stair. With short fibers, I didn't mention that. So, but coming to the latest and new project we are doing now, and I'm quite happy about this. So it's an outdoor stool, and it's the first time that we combine now the geopolymer with a biochar. Biochar, to explain briefly, is a method of storing CO2 through a pyrolyse, storing basically natural matter that is already there, that if it would rot outside, it would just create CO2. So you actually capture the CO2 in this coal, in this biocoal. There's biochar, and there's companies who do this, and they offer this product to the industry for, to now store this material. And we will have more details later on the performance in the LCA, but we did a first object, in this case, an outdoor furniture, which has 13% of this biochar in it. So that's the mass percentage. So volume percentage is 50%. So we actually put 50% of coal, because it's lightweight, into this object. And this is the one you can see here. And it's also not so heavy as normal concrete because of the coal. So I can lift it. Normally I would probably not so easy be possible. You see the coal parts here at the top as well. And for sure we used our formworks, 3D printed formworks. And I'm quite happy about the result. So it's really just also to make a statement that's possible to charge now a building component with this biochar, and to actually get a CO2 footprint that is 0 or maybe even minus. So this is something we are now really investigating on. So we are looking into LCA calculations. And so for this, just to add, being in the principle of what we are changing now in the formulation, we just add the biochar to the geopolymer. So the geopolymer already being very low in the CO2 emission, plus the biochar coming on top. And this project is done in cooperation with the ISMD, with Emanuel Novak. So I would like to come on stage. Emanuel, thanks for joining.
Thank you, Jörg. I want to explain this chart directly to you because it's highly controversial. And first of all, we're not doing any greenwashing. And second, it's highly complex. So if you want to know a little bit more about it, we can have a quick talk after it. What you can see on the right, this material has a footprint. So the production and also the transport, so the stages A1 to A4, emits CO2, what you can see on the right side. But the biochar gets CO2 certificates as well. What's saying here, it's getting GWP, a global warming potential biogenic, which is highly negative for biochar. So in the European norm 15804, they're saying that the biogenic GWP accounts for the amount of CO2 absorbed from the atmosphere and is bounded throughout the material's lifespan. So with this highly negative biogenic GWP, you can add it together, but at the moment it's not allowed because the norm thinks that after the end of the product, the CO2 evaporates. But the material or the biochar, which is bounded in here, is stored permanently. So for geological lifespan. So it will not be emitted after time, and the norm will change in future. So you can maybe not saying it, you cannot say it has a negative impact, but of course you're storing more CO2 than you're emitting with this product. But for more questions, we can talk a little bit in the coffee break.
Yes, thanks, Emanuel. So that's also from my side, from our side, our talk, and yeah, open to questions.
CO2 negative questions here.
Thank you for the presentation. Do I understand it correctly that the stairs are made from cast geopolymer, the steps in the stair?
No.
Okay.
Sorry, if that would have been misunderstood. So the stair was made from a classic or UPHC, so ultra high performance concrete with metal fibers as a reinforcement. So as you can imagine with this geometry, you cannot place standard rebar. We thought about this for sure. In the top part you could, but we then decided to use the fibers. And this was for sure a challenge first in bringing the concrete into the mold to let's say distribute it evenly, but also having the strength test that I mentioned. The crack test was luckily positive. So in a way that these fibers were enough because the design was also form active. So there's a lot of tension, pressure elements, but there was one part which was already clear, which is the, let's say, weak part, and it could withstand. So, and that's also kind of to be seen in the presentation. The 3 projects I showed is breaking it down to coming to a more sustainable way using a material that has hopefully the performance of a maybe even OHPC, but being, let's say, more sustainable in the resources that we're using now.
Thank you.
One more question.
Okay. The geopolymer material, what is it like to work with it? Is it liquid like concrete in a fresh state? Is it printable?
Yeah, it is actually printable. And the company we work with, they provide for 3D printing, and it's also used. I think it was even shown today that geopolymer is printed. I think ETH is also using it on a couple of projects. So I think it even started with the printing idea, but it gets more and more into different products because it is very convincing. And it is really like a concrete. You can imagine. So the difference of the material matter, the powder, you could say, and the glass as a fluid matter, when you mix it, you first mix it, it's more or less like mixing the cement with the water. And then you add the gravels, you add the sand. And what is to point out in casting, it's really an advantage because you can put sand and gravel in a huge amount into it, as we could see, because the biochar that we added was really in a gravel form. So this is something you cannot do in printing. But on the other hand, the gravel and the sand brings a very positive CO2 footprint, depending on from where you get it, if you get local materials. So this, I think, is still interesting to look at it in terms of should it be casted, should it be printed, and this is anyway our approach. So we always say that if it's better to cast it, for example, the 10 windows, what is my next task to really make a calculation? If we would be able to print it, and we will soon be able to print this directly with a high resolution, is it more feasible or also sustainable to print the 10 or to print one form and cast the 10? So I think this is really a question that, will come up in the next years or days.
Jörg Petri, thank you very much for your presentation.
Yes.